All right, let's talk about one of the biggest headaches in machine learning. How in the world do you pick the perfect features for your model when you have like thousands of options? If you get this right, your model is an absolute superstar. But if you get it wrong, well, it's a total dud. So let's figure out how to get it right every single time.
Think about it like this. Imagine you're trying to bake the world's greatest cake, but your kitchen has thousands, maybe even millions of possible ingredients. In our world, those are features. Now, some combinations are going to give you a masterpiece, right? But most are going to be, well, a disaster. So how do you find that one perfect, prize-winning recipe without spending a lifetime baking every single possible cake?
And this is where the math just gets insane. If you have n features, the number of combinations isn't n. It's 2 to the power of n. Just 30 features? That's already over 1 billion combinations. If you have 100 features, that number is bigger than the number of atoms in the known universe. So yeah, trying every single one is not just a little impractical, it is fundamentally impossible.
And this, my friends, leads us to what I like to call the feature choice crisis. We are staring down an absolutely astronomical search space, and we desperately need a smarter way to find that golden ticket, that one optimal set of features for our model.
So, okay, brute force is out. It's just not going to work. We need something smarter, right? A more elegant way to search. So what if we could borrow a strategy that's been solving complex problems for, about 4 billion years? What if we look to nature itself for the answer?
And that is exactly what we're going to do. The solution we're talking about today is this brilliant method modeled directly on the principles of evolution and natural selection. It has a name, and it's called a genetic algorithm.
At its heart, a genetic algorithm is basically just survival of the fittest, but for our data. We start with a whole bunch of random feature sets, and then over many generations, the best ones, the fittest ones, survive, they combine, and they create even better offspring. We are literally evolving our way to the perfect solution.
Okay, so how does all this biology lingo actually map to our machine learning problem? Well, a chromosome, that's just one possible combination of our features, usually written as a string of ones and zeros. Each little piece of that, each gene, represents a single feature. A 1 means we include it, a 0 means we leave it out. The population, that's just a big collection of all these different chromosomes, all our potential solutions. And the most important part, fitness. That's our scoreboard. It's simply how well our model performs using that specific set of features.
And the parallel here is it's perfect. In the real world, organisms evolve to better survive in their environment. In our algorithm, we're evolving feature sets to create a better predictive model. It's not just a cute analogy, it's quite literally digital natural selection at work. So how does this digital evolution actually happen? What does it look like in practice? Let's break down this step-by-step cycle that takes us from a total mess of random features to a highly optimized, high-performing set. It all happens in this continuous loop. First, we kick things off by creating a random population of feature sets. Next, we test every single one to see how fit it is. Then, we pick the top performers to be our parents. After that, we combine those parents to create a new generation of offspring, and then we just do it all over again, repeating this cycle for generation after generation. Now, the absolute heart of this whole thing is the fitness function. This is our judge, our referee. For every single feature set we create, this function grabs it, trains a model with it, and then spits out a score, say its accuracy. A higher score means a fitter individual, and that gives it a much better shot at passing its genes on to the next generation. So, once we've picked our best performing parents, it's time to create the next generation. And we do that through something called crossover. Just imagine taking the first half of one parent's feature list and sticking it to the second half of another parent's list. Boom, you've got a new offspring that mixes the traits from 2 proven winners, hopefully creating an even more powerful combination. But crossover can only mix and match what's already there. To introduce some real novelty, to find brand new ideas, we need mutation. What happens here is, every once in a while, the algorithm just randomly flips a single gene. A feature that was off suddenly gets turned on, or vice versa. It seems tiny, but this random spark is absolutely critical. It stops the population from getting stale and forces it to explore totally new territory, which could lead to a massive breakthrough. Okay, so we've been through chromosomes, fitness, mutation, the whole shebang. You might be wondering, why go through all this trouble? What's the real, tangible payoff for running this entire digital evolution process? So what's the big deal?
Well, first, genetic algorithms perform a global search. That means they don't just get stuck on the first pretty good solution they find, they keep looking for the true overall best one. Second, and this is huge, they are incredible at finding complex interactions, groups of features that aren't that special on their own, but are absolute magic together. And finally, they're really robust, meaning they still work well even when your data is a little messy.
And here's the bottom line. After this algorithm runs, sometimes for hundreds or thousands of generations, after all of that ruthless selection, all that crossover, all that mutation, you are left with one thing, the single best performing chromosome, the champion survivor of this entire evolutionary gauntlet. That is your optimized set of features, ready to build the best possible model you can.
It's really an amazing reminder, isn't it, that some of the most elegant solutions to our most complex, modern digital problems are actually hidden in the blueprints of the natural world. It just leaves you with this one big question. What other massive challenges could we solve if we just took a little more inspiration from nature's 4 billion-year-old R&D department?